Okay, so let us start 11th standard mathematics, and we are going to start with set theory. Set theory, as you may already know, was developed mainly by the German mathematician Georg Cantor. Cantor is the man who showed us that there are, in a very precise sense, more real numbers than there are natural numbers. Now, when we try to think about it, it does not really make sense because there are infinitely many natural numbers and also there are infinitely many real numbers. So, how is it that there are more real numbers than there are natural numbers? There is a precise sense in which this is true. But at the time Cantor made his discovery public, the other mathematicians, the contemporary mathematicians, attacked him, they ridiculed him, they criticized his discovery, and in fact made his life hell. Cantor's story is a very tragic one, but nevertheless he gave us this extremely beautiful idea of sets, and especially infinite sets and their sizes. He is the one who showed that there is not just one infinity, but there are infinitely many different sizes of infinities. The set theory we are going to see here, in fact, is known as naive set theory or beginner's set theory, if you put it in simple words. There are other more advanced level set theories as well, which rectify some of the shortcomings of this beginning set theory. It is beginning set theory and it is naive set theory because here we take the word set as we know it. It's a collection of objects, okay. However, it turns out that this careless use of this notion as a collection of objects, later on it gives birth to some problems, some paradoxes. In order to get rid of those paradoxes, other advanced level set theories have been developed. We, however, won't see those things here. Okay, so let us see what this is all about. Now, you already know the meaning of this word sets or set. It is actually nothing but just a collection of some objects, that's it. And in everyday life we come across many different types of collections. For example, the collection of all furniture in this room, the collection of all people in the world right now. Some such things we keep on getting and we do not even give it a second thought. A collection is after all a collection. In mathematics also, there are many different collections. For example, in the text we see these collections. Let's see them one by one. The collection of, because we have to write again and again the collection of, that's why these collections have been written like this. You can add this, the collection of, in front of all these sentences, all these collections, okay. So the first one is the collection of all odd natural numbers less than 10. And so the objects in this collection are these numbers. These are odd numbers, they are natural and they are less than 10. 1, 3, 5, 7 and 9. The next collection is not really very mathematical, but nevertheless it's a collection. The collection of the rivers in India. It's a legitimate collection. Then the third one is the collection of all the vowels in the English alphabet, A, E, I, O and U. The fourth one is the collection of various kinds of triangles. The fifth one is the collection of all prime factors of the number 210. That is those numbers which are of course positive. Generally when we talk about factors, we do not think of negative numbers. although negative factors are still there, but we ignore them here. Okay, the positive factors of 210 which are prime numbers, and it turns out that they are 2, 3, 5 and 7. And lastly, the collection of the solutions of this quadratic equation x square minus 5x plus 6 equal to 0. And if one solves it, one easily sees that the solutions are 2 and 3. So these are the two objects in this collection. The text also says that these collections are all well defined. Now, what do we mean by well definedness? This is very important to understand what this word means, because we only consider well defined collections in mathematics. A collection of some objects is called well defined if, given any object whatsoever, there is no confusion in deciding whether the object is an object in the collection or not. For example, it is clear what the objects in the first collection are. They are precisely these numbers. So, if I am given any object, say I take a triangle in the plane, that is definitely not an object in this collection, because we do not have any triangle as an object in this collection. However, if I take the number 1, then I can clearly see that 1 belongs to this collection. So, this collection is well defined in the sense that I know precisely what the objects in this collection are. And as a result, I also know what objects do not belong to this collection. In other words, I know the collection fully without any confusion. In that sense, it is well defined. The second one also is well defined. We know precisely what the rivers in India are. Okay, we can in fact list them. This is also well defined. Just like that, we know precisely what the vowels in the English alphabet are and what the consonants are, for that matter. This is also a well defined collection. The fourth one is a little doubtful. Okay, it's not said here that we have to consider all the types of triangles. It's given that simply various kinds of triangles have been taken, and that is the collection. So this one is a little doubtful. I don't think we should call it a well-defined collection. However, the text says that it's well-defined, but I'm not buying that. Okay, this is a little doubtful. The fifth one is, of course, it is also well-defined. These are precisely the prime factors of 210. So they are precisely the objects in this collection, nothing else. Okay. For example, 13 is a prime number. However, 13 does not belong to this collection because 13 does not defy to 210. We are not only considering prime numbers but those that defy to 210, and moreover, we are considering only positive primes. Usually the negative counterparts of prime numbers, although they are prime, but they are not considered as primes. Okay. Technically they are primes, but when we say prime numbers, we mean positive primes. And the final one is the collection of the solutions of this quadratic equation. We know precisely that 2 and 3 are the only solutions, nothing else, not 1, not 0 or anything else. So these are examples of well-defined collections. Now let's see one collection which is not well defined. And in the text it's given that, what was it? I forgot. Oh yes, the collection of 5 most renowned mathematicians in the world. This collection is not well defined because the criterion for deciding if some mathematician is renowned or not is not definite. Someone who is renowned for you may not be renowned for someone else. Okay, it becomes a subjective choice. There is no objectivity in deciding which mathematicians should belong to this collection. For example, I would like to say that Ramanujan belongs to this collection, and very few people will refute me because he is a well-known mathematician. But if I say want to include someone who is well known but in a small region, then that will become debatable. That's why this collection is not well defined. And we do not consider such collections in mathematics simply because there always is a doubt of what objects belong to the collection and what don't. Okay. And that is why we only consider well defined collections, and they are called sets. A set is a well defined collection of objects. And we only consider well defined collections. Now, before I erase this part, let us also see more specifically some statements about these collections regarding their well-definedness. For example, this collection, the rivers in India, is well-defined. We know that the Nile River in Egypt is not an object in this collection. However, the river Ganga or Yamuna, okay, these are rivers in India, so they belong to the collection. Similarly, we know that, say, U belongs to the collection of all vowels in the English alphabet. However, Y is not an object in this collection. Okay. Or for example, the letter C is not an object in this collection. Alright, so now that well-definedness of a collection is clear, we can move on. We need to write a lot of things. I mean, if we stick to English sentences, then we need to write long sentences while discussing about these things. That's why in mathematics we develop symbols, we define symbols so that we can shorten a statement. And one such symbol is this belonging relation. Okay. Should I say those things first? Yeah, before saying this something about this belonging relation, let us also see some collections which have some reserved symbols for them. Some names have been given to them. So when you see those symbols, you will have to understand that we are talking about that collection. And now of course we can quit calling these things collection because we can call them sets. We are going to consider only well-defined collections and they are sets. Some important sets in mathematics. and the symbols that go with them. This symbol denotes the set of all natural numbers. Now this n may look a little strange. Actually this is the symbol that is reserved for the set of natural numbers. However, it's a little difficult to keep writing this. You can instead write ordinary n. In the text, a bold n has been written, but you can just write n, okay? And you know what these numbers are. The counting numbers. Okay, and they do not end. That is also something we already know. They keep on going to higher and higher numbers, 4, 5, 6, and so on. Then comes Z, the set of all integers. These are integral numbers, non-fractional numbers. They can be positive or negative, and there is 0 of course also. So these are the integers, and the set of them is denoted by the letter capital Z. Z comes from the German word zählen, which means to count. Q, again I am repeating, you do not have to write this Q, okay? You just simply write capital Q here, capital Z here, or Z, okay? If you are following American English, you would call it Z. The set of all rational numbers. And you also know what rational numbers are. They are numbers of the form P over Q, where P and Q are integers and Q is not equal to 0. You see, we have a very bad tendency of remembering this definition of rational numbers incorrectly. We tend to say that a rational number is a number of the form P divided by Q, where Q is not equal to 0. We leave out the part that P and Q have to be integers. You be careful with this, okay? They have to be integers, because otherwise this is also a rational number. You can write it in this form where 1 is not equal to 0. The crucial part that P and Q both have to be integers should not be forgotten, okay? Then of course we have R, the set of all real numbers You know what real numbers are. They include all the rational numbers as well as some numbers which are not rational, which are called irrational numbers. And then the positive counterparts of these last three sets. The set of all positive integers. Which if you see carefully is actually nothing but this set. Okay, Z plus means just n. Q plus the set of all positive rational numbers. Oh, by the way, the letter Q stands for quotient of two integers. That's why it's called Q. And R, of course, stands for real, positive rational numbers. And like that, we also have R plus the set of all positive real numbers. Whenever you see these symbols and nothing else will be said, you have to understand what sets they represent. Besides these sets, there are other sets which are important, but that will come later, okay, not right now. Now there are some things, some points regarding these notations and these symbols that we will use. Let's just see these points. Yeah, I had all these things in between. I forgot and I jumped ahead and I was going to say something in advance. No, we first of all, let's just go with the flow and don't just skip anything. So there are these 3 points. The words object, member, and element of a set, or we can put the plural forms also. Elements of a set are used synonymously. That is, they are supposed to have the same meaning. When we say that something is an object in a set, it means that that thing belongs to the set. It also means the same thing to say that that object is a member of the set or is an element of the set. So you can use any of these 3 words. However, it's more common to use elements. Okay, so that's what we will also do. Number 2, sets are usually denoted by capital letters, capital Latin letters, such as A, B, C, X, Y, Z, etc. And the elements in a set are denoted by small Latin letters. The elements in a set or the elements of a set, same thing, same meaning, are denoted or written by small letters writing capital letters, I put capital C. That's not needed. A, B, C, X, Y, Z, etc. However, there is an exception. Sometimes some sets are also denoted by small lowercase Latin letters. I won't say where right now. Somewhere in advanced mathematics, you will come across a situation where a set will be denoted by lowercase letter. So it happens, okay, for some reason. Elements, however, are consistently denoted with small letters only, but there are exceptions to this also. Right now, we do not have to think about those exceptions. For us, capital letters mean sets and small letters mean elements in sets. There is something else also I want to say here at this point. We denote consistently by this symbol in the set of natural numbers. However, the term natural number itself has two different meanings. For in most of the places, it means these numbers, and we do not include 0 in this collection. However, some people also include 0 and consider these numbers, and they call these numbers natural numbers. It's just a matter of considering or not considering 0 as a natural number. Okay, it does not affect the resulting mathematics in any way. It's like what example can I give? It's like calling someone who stays outside of this country, outside of India, an Indian. Okay, their origin is India, however, they have gone outside and settled there. Now, whether you want to call that person Indian or not, Indian origin we say, however, you may choose to call that person Indian or not. That is up to you. That is not going to change anything. Okay. It's like that. Some people call 0 also a natural number. In this text, however, we will not say that 0 is a natural number. For us, 0 is not a natural number. For us, the natural numbers start from 1. Alright. Let us now come to that part where we are going to talk about notations that will make our life easier. We will not have to write again and again 1 is an element in n. There are symbols for that. If A is an element of a set capital A, remember that small letter means element and capital letter means set. Then we express this by writing a symbol like this. We first write the element and then we write the set, and in between we write a symbol like this, which is actually the Greek letter epsilon. And we read it as A belongs to A. Okay. So when you see this, when you want to read this, it means this: A belongs to A. If an object if an object B is not an element of a set A, then we write this. Okay, we strike that epsilon. B is not a member of A or not an element of A, and that is expressed by writing this symbol. Okay. Now, something else about the notation that I have just simply remembered. We have just now said that we use capital letters to denote sets and small letters to denote elements, and I have mentioned that there are exceptions to this. There are situations in which small letters also denote sets, but that we do not have anything to do with that. However, there is a situation in which capital letters will denote elements. How? Let us see. Suppose you consider the set whose elements are these. Whose elements are these four sets. Okay, so this set, which is, it is the collection of these four sets, that can also be considered, but note that here the elements themselves are being denoted by capital letters. So it can happen. However, if we are just simply saying an abstract element, say A or X, in that case we won't use capital letters, we will use only small letters. So let us now see some examples of this notation, this symbol. For example, if capital V denotes the set of all vowels in the English alphabet, then A belongs to V, because V has A as an element. I belongs to V, U belongs to V, but Y does not belong to V. B does not belong to V. These are consonants, and say Z also does not belong to V. Okay, so that's how, instead of writing again and again I is an element of V, U is an element of V, we can shorten those sentences by using this symbol. We have to say these things so many times that devising such neat notations is necessary. Okay, it's not merely that we are doing like this or we have devised such notations to make it look fancy. No, it is out of necessity. Also, another example is also given in the text. What is that? Oh yes. Also, if P is the set of all prime factors of the number 30. It's like that one, the set of all prime factors of the number 210. Here, however, we have 30. Then two belongs to P because 2 divides 30 and 2 is a prime number. 3 divides P and 5 divides P. In fact, these are the only elements in P. But 10 does not belong to P. 10 divides 30, so 10 is a factor of 30, but 10 is not a prime number. 7 does not belong to P. 7 is a prime number, but 7 does not divide 30. And like that, 15 does not belong to P. 15 divides 30, but 15 is not a prime number, it's a composite number. Alright, now you may have noticed one more inconvenience. You can see an example of that inconvenience here. If V denotes the set of all vowels in the English alphabet, is it really feasible to keep on writing such long sentences? No. So we need some way of specifying the elements of a set, some notation like this, some short notation. Using that we can express such long sentences more briefly, and there are two ways of doing this. There are two methods or ways of representing or specifying sets, which essentially are ways of shortening sentences. The first one is roster or tabular method, and the second one is set builder or rule method. So let us first see roster method. In roster method, the elements of a set are listed, are separated by commas, and the list is enclosed within curly brackets. Okay, it's a little difficult to understand this at once, so we need some example to illustrate this. And let me not give arbitrary examples. Let me stick to the text. Okay, what is given in the text? Yeah. For example, Yeah, why not write from there? For example, the set of all even positive integers or even natural numbers, same thing, less than 7 in roster method is written as this. Okay, so let's follow this, whatever is written. We list all the elements. So what the elements are in this set? The positive even integers less than 7, 2, 4 and 6. You may notice that when writing such a list, we automatically already put commas to separate the elements in the list. So we do so here as well. And then enclose the list within curly brackets. It's important to remember that we have to use only curly brackets. Okay, curly brackets have been reserved for sets. We do use other brackets also in some situations, but that is different. Also to denote sets, but those are special types of sets. They will come, but we still have time. Okay, so this is roster method. Let's see another example. In roster method, the set of all positive factors or divisors, same meaning, of what is the number here, 42 is. So you need to write all the positive divisors of 42. Now let me just show you something. 42, it has some positive divisors, okay. It's not exactly as easy as say 6 or 2. So what we do when we are to find all the positive divisors of a given number. What you do, you start with 1. 1 of course is a positive divisor. 1 divides everything. So 1 also divides 42. Whenever you get one positive divisor, you divide the number by that positive divisor, you get another one. Divide 42 by 1, you get 42 itself. The next one is 2. 2 divides 42. Okay. Divide 42 by 2, you get 21. So this is another divisor. What can be the next one? 3 also divides 42. Dividing 42 by 3, you get 14. 4, does 4 divide 42? No. 5 of course also does not divide 42. 6 divides 42. And when you divide 42 by 6, you get 7. And then if you want to continue, you get 7. And actually, the other divisors are, you have already got them. That's how you can quickly find all the divisors. Now the set is this. Alright, now comes two aspects of writing or specifying a set in roster or tabular form. You may have noticed that we have taken great care in listing these elements as if we are following a particular order in writing the elements from the smallest element to the largest element. However, in a set, order is immaterial. It does not have any significance. Why? Because a set, after all, is a collection of objects. It does not matter whether you mention this as your first object, this as your second object. In a set, there is no first, second, or anything. It's just the collection of those objects. What matters is what objects are elements of the set and what objects are not. That's what matters. So, the order of the elements in a set written in roster method is immaterial. You can choose any order to specify a set in roster method. So, for example, and let's not write this big one, okay, let's just write that one. The set whose elements are 2, 4 and 6 is also the same as the set whose elements are 4, 2 and 6 and so on. You can write many, actually 6 different ways of writing the elements, changing the order. It does not matter how you write the elements in roster form. Okay, now these sets that we have written in roster form are fairly small so that we can list all the elements. However, if the set becomes really very large, then we have to use ellipses, those 3 dots that we use when we want to suppress some things in a sentence. Say you do not want to write everything, and whatever you are suppressing or whatever you are not writing, it's understood. Okay, then you use these 3 dots and they are called ellipses. And remember, 3 dots, not more than that. If some sentence or something is ending with an ellipsis, then besides 3 dots, you also put a full stop or period. Okay, so you see 4 dots, but those 3 dots indicate the fact that some things are not being said, however they are there in the background. Now an example where this will be used is this. The set of all natural numbers less than 100, say. Now it is impractical to write, of course you have to write in roster form this set, but it's impractical to write all of the elements, show all of the elements. Instead we use ellipses like this. Now a question arises. How many elements should you actually write? You can see that we have started, of course, order is immaterial. So I could have also written 99 here. However, because I am not writing everything, so I need to show some type of pattern in which those elements that I am not writing, they follow that pattern so that we can know what we are not writing, what the elements are that are hiding in the background. However, in this way of writing, I have chosen to start with 1 naturally. I have written 3 elements here then I have used ellipses, and then I have written 2. There is no hard and fast rule as to how many elements you have to show and how many you will hide. Okay, you can also write this same set as this. Because the pattern is clear. After 1, 2 is coming, so after 2, 3 should come, like that. However, too few elements will make the thing somewhat difficult to understand. For example, if you just simply read, this is also written sometimes. However, it becomes less and less clear if you mention less and less elements. It becomes more and more vague. So it's up to you to decide how many elements you want to show and how many you do not want to show. However, in such cases, the point is that ellipsis is used, because if writing, you see, this is one case in which the sentence is smaller than the notation. The sentence is just, it's precise, the set of all natural numbers less than 100. However, if you are using roster method and you are using all the elements, that becomes unmanageable. That's why we have to use ellipses. And especially using ellipses becomes absolutely necessary when the number of elements is infinite. For example, the set of natural numbers itself will be written like this: ellipsis, and that's it. You cannot write, there is no natural number where things are going to stop. We do not have anything like that. And you may also have to use ellipsis more than once. For example, the set of integers is written in roster form sometimes like this: ellipsis -2, -1, 0, 1, 2, and then again ellipsis. Or some people would like to write that set like this as well. However, at this stage, this one is more apt. Okay, this one is also a legitimate representation of the set of integers in the roster method, but you stick to this. So this is one aspect of writing sets in roster method. One aspect means I am talking about the insignificance of the order in which the elements are written. And of course, we use ellipses when the set is very big. But there is another aspect also. Repetition of elements in a set written in roster method, written using roster method, is allowed, but does not serve any purpose, and so is discouraged. while writing a set in roster method and while listing the elements, you can repeat an element as many times as you want. Okay, that is allowed. However, that does not give us anything. If anything, it just creates unnecessary writing labor, and that is why that practice is discouraged. However, elements can be repeated naturally. Such situations also are there. For example, but whenever you see an element being repeated in a set, we do not repeat that. Okay, we write only one instance of the element and we do not write the repetitions. The example will make these things clear. The set of all letters of the word school is what? In roster form, of course, it will look like this. S C H O O L. However, note carefully that it is the set of all letters of the word school. The letter O is repeated. It appears 2 times in this word. However, when we are talking about the letters of the word school, that repetition does not matter. So, we do not write that O. Although this is not anything wrong, it's okay, but there is no need to write O twice. And in fact, more properly, these are the letters in the word school. We have the letter S, C, H, O and L. Okay, so that's how repetition does not serve any purpose, and that's why we do not repeat. So that is your roster form or tabular form. Oh, by the way, the method is called roster method, and once you have specified or written a set using that method, that set is said to be in roster form or tabular form. Okay. And the second one is set builder method or rule method. In this method, we write a general element of the set as a variable, okay, x or y something, followed by a colon which denotes the phrase such that, and then a condition or maybe several conditions is written which that general element is supposed to satisfy. And the collection, like the roster method, is enclosed within curly brackets. That curly bracket part is constant. It's there in both the methods. And the collection is enclosed within curly brackets. Now what is this? An example will make it clear. The example that has been chosen will, how many examples are shown here though? 3, only 3, okay, anyway. So the first one is, let me first write the set and then we will see what it means. X is a natural number and 3 is less than x and x is less than 10. Alright. So what is this set? But before that, let's see what this part says. In this method, we write a general element of the set as a variable, some symbol, some x, y or z or anything in fact, followed by a colon, and the colon denotes the phrase such that. And then after the colon, we write a condition or a set of conditions that general element is supposed to satisfy. And the entire collection is enclosed within curly brackets. For example, this one. So that general element here is x. It's a variable. It denotes an element of the set A such that x is a natural number and x has to satisfy these inequalities. You can understand what the elements of this set are. They are 4, 5, 6, 7, 8 and 9. These are precisely the elements of the set. So instead of enlisting them, instead of writing a list for them and writing the set like this, like what we do in roster method, we write a general element such that this is the condition that general element has to satisfy. And the set is the collection of all such elements x for which this is true. And in fact, this whole sentence is written like this. Is read like this. A is this equality is for is. A is the set of all elements x such that x is a natural number and x satisfies these inequalities. At this method, you can clearly see it will in fact further shorten many sets for which it's a little difficult to write in roster method. You can conveniently write those sets in this new method, set builder or rule method, and we call it rule method because this part of the set has that rule or condition that the general element x has to satisfy. Okay, now there are many different ways of writing this particular set. You can change the style of writing. You can make it even more condensed like this. Instead of writing x is a natural number, you can write this so that you do not have to write that sentence, and this. This is briefer, more convenient. Or you can also discard this and use comma. And in fact, you can make it even shorter. by writing like this. Because we have to write the general element here, if we have any condition that the element has to satisfy, especially by condition I mean this kind of condition, that the element is coming from some already given set. Instead of writing like this, you can write like this. Here itself you write this condition. So you are writing the condition on one hand and showing the general element on the other hand simultaneously, such that now you can of course ask me why you should not write this one here and that one there. Well, that is not done generally. The more you see these examples, you will realize what you can write and what you cannot write. We do not write some such conditions which, I mean, in this part, you either write the variable element x or the condition that x belongs to some set. Okay, that is the general practice. So, many different ways of writing the same set in set builder method. And in set builder method, this next set can also be written like this. It is that set V, the set of all vowels. Oh, and by the way, here it's not necessary to always use X. You can use any letter, for example, Y. Y is such that Y is a vowel in the English alphabet. However, do not write here A, E, I, O or U, because if you do that, it is no longer a variable. This Y is denoting all of those vowels simultaneously. However, you do not write a vowel itself here. You write anything else, okay? And there is another one. Yeah. Z such that Z is an odd natural number. There is not many different ways of writing this set B in set builder form. This one, however, you can shorten just like the set A by changing the writing style. So here the set consists of all odd natural numbers. You can write like this. Z is a natural number and Z is odd, or following this practice, you can write like this. 2 does not divide Z. Oh, by the way, this notation, probably you already know, but still, for 2 integers A and B, we write this when we want to say that A divides B, or more precisely that B is divisible by A. For example, 2 divides 4, but 3 does not divide 4. So to write does not divide, we strike that vertical bar. If Z is not divisible by 2, being divisible by 2 means being even, being not divisible by 2 means being odd. Or you can also write like this. z is equal to 2m minus 1, where m is a natural number, because the odd natural numbers look like this, 2m minus 1, where m is a natural number. You can realize why that is so. You take m equal to 1, 2 minus 1, you get 1. You put m equal to 2, 4 minus 1, you get 3. Put m equal to 3, 6 minus 1, you get 5. 1, 3, 5, 7, 9, like that you keep getting. Okay, so these are some different ways of writing the same set C in set builder form. Now after this, of course, we have some illustrative examples that we will discuss in the next part. Okay, so let me just finish it here itself. So see you in the next part. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.